Welcome everyone to Gen AI Learner. Today we are going to explore a paper that I think will fundamentally change how you think about GPU resource management. The paper is titled, Towards Efficient and Practical GPU Multitasking in the Era of LLM. Before we dive in, let me ask you a question. When you train or serve a large language model, how much of your GPU do you think is actually being used at any given moment? Take a moment to think about it. Most of you probably guessed somewhere between 60 and 80%. The reality, as this paper shows, is often less than 20%. That is the central problem this paper addresses, and by the end of today's lecture, you will understand exactly why this happens and what we can do about it. Let me show you the core motivation for this paper. We have seen a more than 1,000-fold improvement in GPU compute and over 20 times expansion in memory. Yet, when you run Llama 3-8B on an A100 GPU, both memory usage and SM occupancy hover below 20%. Here is my question for you. If you had a 1,000 times more powerful machine, but only used 10 to 20% of it, what would you call that? That is right. It is a massive waste. This is the single-tasking problem. The GPU is reserved for one task, and that task simply cannot keep the hardware busy all the time. The paper argues we are at an inflection point. Just like CPUs moved from single-tasking to multitasking decades ago, GPUs must do the same. So why is single-tasking becoming structurally unsustainable? The paper identifies 3 key trends. Let me ask you to think about each one. First, if you have a model with only 1 billion parameters running on a GPU with 80 gigabytes of memory, what happens? The model simply cannot use all that hardware. Second, think about how LLM inference works. In autoregressive generation, you do not know in advance how many tokens it will produce. This means memory usage is highly variable and unpredictable. Third, modern AI systems are not single models anymore. They are compound systems, each with different resource needs. Running them all in single-tasking mode creates an inefficient patchwork of underutilized GPUs. The solution? Multitasking, sharing GPU resources across multiple workloads simultaneously. Now let us think about what a good GPU multitasking system actually needs to do. The paper identifies 4 requirements, and I want you to notice something important. These requirements are in tension with each other. Here is a question. If you share a GPU between 2 tasks to improve utilization, what might happen to the performance of each task? Right, they might interfere with each other, degrading performance. So high utilization conflicts with performance guarantees. The key insight the paper offers is that this tension can be resolved through fast, fine-grained, on-the-fly resource partitioning. If you can dynamically adjust resource allocation in real time, you can give each task exactly what it needs when it needs it. Fault isolation and large-scale deployment are equally important for production systems. Keep these 4 requirements in mind as we go through the rest of the paper. Let us look at Table 1, which is one of the most important contributions of this paper, a systematic evaluation of every existing GPU multitasking technique against the 4 requirements. I want you to study this table carefully. Notice the pattern. Every row in the ideal column has a check mark, but no existing technique achieves all 4. Let me ask you, why do you think MIG, multi-instance GPU, which is NVIDIA's official product for GPU sharing, fails on high utilization? Because MIG statically partitions the GPU into fixed-size slices. If you give a tenant a quarter of the GPU, and they only use half of that quarter, the rest is wasted and cannot be reclaimed. Now look at the fault isolation row. Notice that most research works fail here. Why? Because they use MPS multiprocess service, which merges multiple processes into a single shared CUDA execution context. When one process crashes, it can corrupt the shared context and crash everything. This is the fundamental tension. Spatial sharing improves utilization, but sharing a CUDA context destroys fault isolation. The paper's central contribution is showing how to escape this dilemma. The paper's central proposal is elegant in its analogy. We need a GPU operating system. Think about how your laptop manages CPU resources. You can run dozens of applications simultaneously, each getting its fair share of CPU time, with memory isolation between processes, and if one application crashes, the others keep running. We have had this for CPUs for decades. The paper asks, why don't we have this for GPUs? The proposed GPU resource management layer is exactly this. A software layer that intercepts GPU API calls, manages resource allocation dynamically, and provides isolation guarantees. Here is a question to think about. Why is building a GPU OS harder than a CPU oxygen monosulfide? Pause. Several reasons. GPUs lack hardware support for virtual memory page faults. CUDA's execution model assumes one task owns the entire device, and the memory access patterns of LLMs are highly dynamic and unpredictable. The paper addresses each of these challenges in the following sections. Let us go through them one by one. Now let us get into the technical details of compute multiplexing. There are two ways to share GPU compute: temporal and spatial. Think of it like time sharing versus space sharing on a CPU. In temporal sharing, one task gets all the SMS for a time slice, then the next task gets them. In spatial sharing, multiple tasks run simultaneously on different subsets of SMS. Here is a question. Which approach do you think provides better fault isolation, and why? Pause. Temporal sharing. Because each task runs in its own CUDA context. If one crashes, the others are unaffected. Spatial sharing typically requires merging tasks into a shared CUDA context, which destroys fault isolation. Now here is the key insight about temporal sharing for LLMs. You might worry that context switching every few milliseconds would add too much overhead. But look at the numbers. Llama 3-8b completes all its kernels within 10 milliseconds at batch size 8, while end-to-end inference takes seconds. So the switching overhead is negligible. The paper also proposes using a library called libs-mcontrl to implement spatial sharing at the driver level. This is elegant because it is transparent to applications and does not require modifying kernel code. Memory multiplexing is where this paper gets really interesting, especially for LLM workloads. Let me ask you a question. In a traditional convolutional neural network like ResNet, if I tell you the batch size, can you predict the memory usage? Pause. Yes, almost exactly. It is deterministic. Now, what about an LLM serving system? Pause. No, you cannot, because the output length is unknown until generation is complete. This is the fundamental challenge. The paper proposes using CUDA's recently released virtual memory APIs to implement demand paging for GPUs, similar to how CPU operating systems handle virtual memory. The key idea is to intercept CUDA-malloc calls at the driver level and replace them with virtual memory operations. This is elegant because it is completely transparent to the application. There is a subtle challenge though. Frameworks like PyTorch maintain their own memory caches and do not always call deallocation APIs when they are done with memory. So the system cannot tell which memory is actually free. The solution is to hook into PyTorch's custom allocator interface. This gives the system semantic knowledge about which memory is truly inactive and can be safely reclaimed or swapped to CPU DRAM. Now let us look at Figure 2, which illustrates a key insight about resource allocation. This graph shows two kernels, kernel 1 and kernel 2, and how their performance, measured as compute utility, changes as you allocate more SM cores to them. Look at kernel 1. Its utility increases almost linearly with SM allocation. Now look at kernel 2. It saturates quickly. After about 60% SM allocation, giving it more cores barely improves its performance. Here is my question. If you have spare SMS to allocate, which kernel should you give them to? Pause. Kernel 1, of course. It will make better use of them. This is the utility-guided policy. Instead of simply dividing resources equally, max-min fair scheduling, the system measures each kernel's marginal benefit from additional resources and allocates accordingly. The paper also introduces the concept of guaranteed versus preemptible resources. Guaranteed resources are like reserved seats on a train, always available. Preemptible resources are like standby seats. You can use them when available, but you might need to give them up. This two-tier model elegantly resolves the tension between high utilization and performance guarantees. Fault isolation is perhaps the most subtle but critical requirement for production GPU multitasking. Let me explain the CUDA context problem with an analogy. Imagine you are sharing an office with several colleagues. In temporal sharing, each person has their own private office. If one person's computer crashes, it does not affect anyone else. In MPS-based spatial sharing, everyone shares a single open-plan office with one shared computer. If one person accidentally deletes the operating system, everyone loses their work. This is exactly the CUDA context problem. Here is a question. If you were designing a solution, what would you change? Pause. The paper's insight is that this is a software problem, not a hardware limitation. Modern GPUs already have multiple independent compute engines and memory controllers. The hardware can support isolation. The software just does not expose it. The proposed solution is to track which hardware components are assigned to which kernel at the driver level. When a fault occurs, the driver can identify exactly which process caused it. terminate only that process, and let everyone else continue. This is analogous to how modern CPU operating systems handle process isolation, and it is achievable on current GPU hardware with the right driver implementation. Even if we solve all the core technical problems, compute sharing, memory sharing, fault isolation, we still need to deploy this at scale. This slide covers 3 infrastructure challenges that are often overlooked in academic papers, but are critical for production deployment. First, Kubernetes. How many of you have deployed models using Kubernetes? Kubernetes is the standard for cloud deployments, but it was designed for CPU workloads. It treats GPUs as static, integer count resources. You have 8 GPUs, period. Dynamic GPU sharing breaks this model entirely. The paper proposes using dynamic resource allocation, a new Kubernetes feature, to enable flexible GPU sharing. Second, network sharing. When you run distributed LLM inference, you need high-speed communication between GPUs. The challenge is that communication libraries like NCCL do not understand the concept of a GPU slice. They think each physical GPU is a single device. Third, memory bandwidth. Here is a surprising fact. Just 20% of your SMS can saturate the entire GPU memory bandwidth. So even if you allocate only a small portion of compute to one task, it can monopolize memory bandwidth and starve other tasks. These are hard problems, and the paper honestly acknowledges them as open challenges. I want to spend a moment on the open problems section because I think this is where the paper is most honest and most valuable for you as researchers. The authors do not claim to have solved everything. They identify 3 fundamental challenges that remain open. First, security. Even with virtual address space separation, side-channel attacks are possible whenever tasks share physical hardware. This is a well-known problem in CPU security research, think Spectre and Meltdown, and it is equally relevant for GPUs. Second, memory bandwidth control. The workaround of inserting no-ops into kernel code is essentially a hack. It works in theory but is impractical at scale. What we really need is hardware support, like Intel's memory bandwidth allocation for CPUs. Third, network sharing for spatial sharing. This requires changes at multiple levels of the software stack. Here is my challenge to you. Each of these open problems is a potential PhD thesis topic. If you are looking for a research direction in systems for LLMs, these are the gaps. Which one do you find most interesting? Let us discuss this after the lecture. Let me close with the big picture. This paper is arguing for a paradigm shift from GPU singletasking to GPU multitasking. That is as fundamental as the shift from CPU singletasking to multitasking that happened in the 1960s and 70s. Think about how transformative that shift was for computing. Before multitasking, you submitted a job to the computer and waited hours for it to run. After multitasking, you could run dozens of programs simultaneously. The OS managed resources transparently, and hardware utilization skyrocketed. The paper argues we are at the same inflection point for GPUs. The hardware has grown 1000x more powerful, but our software model for managing it has not kept up. The proposed GPU resource management layer, the Open vGPU project, is the first step toward a future where GPU resources are as flexibly shared and virtualized as CPU and memory resources in today's cloud. Before we close, let me ask you one final question. Given what you have learned today, what do you think is the single most important technical challenge that must be solved to make GPU multitasking practical at scale? There is no single right answer, but I would argue it is memory bandwidth control, because without it, even perfect compute and memory sharing can be undermined by bandwidth interference. Think about this as you read the paper yourselves, and come prepared to discuss it next week. Thank you.